6.3, proving identities. Okay, let's do a little startup on non-permissible values. So determine the non-permissible values for the equation tangent of x cosine of x divided by cosecant of x. Okay, so the first part here, cosecant of x, it's in the denominator, so when is cosecant of x equal to 0? Well, 1 over sine of x equals 0. Well, there's no situation where it can have a value of x for sine of x equal to 0, so there's actually no solution here. But be careful. We still have a restriction coming from the cosecant of x, because if sine of x equals 0, then cosecant of x is undefined. So where is sine of x equals 0? That's at 0. So this whole part, sine of x equals 0. That's the inverse sine of 0. So at a reference angle, where is sine of x equals 0? Well, x has to be 0, pi, 2 pi, 3 pi. So this would be 0. And so the restriction on x I get from here is x cannot equal pi n, where n is an element of all integers. Okay, so that's just comes from the cosecant value. Okay, let's look at, so that's the cosecant. Let's look at tangent of x. Remember, tangent of x equals sine of x divided by cosine of x. So I cannot have cosine of x equal to 0. Okay, where's cosine of x equal to 0? That is pi over 2, or 3 pi over 2. So you keep adding pi units, so x cannot equal pi over 2 plus pi n units, and is an element of all integers. This cosine, there's no restrictions. This cosine, there's no restrictions. So our two restrictions are right here. One of them is due to the cosecant, one of them is due to the tangent ratio. Verify that the equation may be an identity either graphically using technology or by choosing one value for x. Okay, let's do both methods. Let x equals pi over 4. So that is the left side, tangent of pi over 4 times the cosine of pi over 4 divided by cosecant of pi over 4. And does that equal 1 minus cosine of pi over 4 squared? Tangent of pi over 4 is 1. Cosine of pi over 4 is square root of 2 over 2. Cosecant of pi over 4, well, that's 1 over the sine of pi over 4. 1 over the sine of pi over 4. That is square root of 2 over 2, or 2 over square root of 2, equals 1 minus the square root of 2 over 2 squared. Okay, and then on the left side, that's square root of 2 over 2 times square root of 2 over 2 equals 1 minus 2/4. That's 2 over 4 equals 2 over 4, and left side equals right side. So that's a check. Okay, graphically, y1 equals tangent of x cosine of x. So just type all of this into your graphing calculator over the cosecant of x. Well, instead of cosecant of x, you can plug in there 1 over the sine of x. So you're just going to have to be careful with your brackets when you're entering this in. y2 equals 1 minus cosine squared of x. And what you're looking for is, do the two graphs coincide when you graph y1 and y2? Of course they do. So this is the y-axis, and then the graph I get looks something like this. And then when you graph, the two graphs will coincide. Okay, so that's how you know that the two identities, the identity is true. Okay, equation versus identity. Let's be careful. An equation is a statement which is only true for certain values of the variable, whereas an identity is a statement which is true for all permissible values of the variable. Cosine of theta plus 1 equals 3/2, where this is the domain, is a trigonometric equation which is only true for, if you solve this, theta equals pi over 3 and 5 pi over 3. 1 minus sine squared versus 1 minus sine squared of theta equals sine theta, cosine theta, cotangent theta is a trigonometric identity that is true for all values of theta, where sine of theta does not equal 0. So you can prove this. Okay, so it's all values versus certain values. Proving versus solving identities. To prove that an identity is true for all possible permissible values, express, so we're on this first bullet, express both sides of the identity in equivalent forms. One or both sides of the identity must be algebraically manipulated, so one or both sides, into an equivalent form to match the other side. Restrictions on the variable must be stated. Okay, so that's why we started with the restrictions. There's a major difference between solving a trig equation and proving a trigonometric identity. Solving a trig equation determines the value that makes a particular case true. You perform equivalent operations on both sides, that is, perform operations across the equal sign to isolate the variable and solve for the variable. Proving an identity is completely different. It shows that the expressions on each side of the equal sign are equivalent for all values for which the variable is defined. That should be sine. Therefore, you work on each side of the identity independently, and you do not perform operations across the equal sign. Recall, identities can be verified using a specific value, but this validates that the identity is true for only that specific value. Graphing each side of a possible identity may show the identity might be true, but it does not prove the identity formally, as it can never be graphed over a domain of all real numbers. Okay, so keep that in mind as we're thinking about solving versus proving. Next page. A little bit more verbiage, folks. Strategies. Okay, these are strategies. We'll go over a bunch of examples that will touch on each of these strategies. Start with the more complicated side of the identity first. So you'll typically see identities when you're asked to prove an identity. You'll typically see one side is more complicated than the other. Work on that side first. Always keep an eye on the side you are not working on, as this becomes your target. Look for opportunities to factor an expression, add or subtract fractions, square a binomial, multiply by the conjugate of either numerator or denominator, or create a monomial denominator. Look for opportunities to use the fundamental trig identities. That's the whole point we're here. Reciprocal, quotient, Pythagorean. For instance, if a quadratic is present, consider Pythagorean identity because you have that degree 2 term. Sines and cosines pair up well, as do secants and tangents, and cosecants and cotangents, because you'll have terms like cosecant of x, cotangent of x. Well, that's 1 over sine of x. This is why they pair up nicely, times sine of x over cosine of x, and you'll get terms that divide out to 1. Okay, so keep these pairings in mind. If the preceding guidelines do not help, try converting all ratios to sine and cosine only. A lot of this will be trial and error. State any non-permissible values. Okay, be careful. These are values which may make any denominator equal to 0. The proof is complete when the expression on the last line on the left side looks exactly the same as the expression on the last line on the right side. So this LS equals RS. Once you get to that point, you do not need to simplify any further. When both sides of an identity are complicated, it may be easier to prove the identity by showing that both sides simplify to the same expression. Technically, the correct form for proving identities is to work on only one side of the identity and force it to look like the other side. You should be able to do this in most cases. However, there may be some identities that you would have difficulty doing this, so you may work on both sides separately. Okay, but that's the key when you're proving separately. Okay. Example 1, tangent of x, cosine of x divided by cosecant of x equals 1 minus cosine squared of x. Prove that it is an identity for all permissible values. So we need to state the restrictions first. So tangent of x where is it undefined? That's sine of x divided by cosine of x. Where is it undefined? Well, where cosine of x equals 0, and those values, we saw this from before, x cannot equal pi over 2, and that varies by pi over n, and is an element of all integers. The other one we saw, this is actually our opening example, cosecant of x. We know that is 1 over sine of x. Well, I can't have a cosecant value that's undefined, therefore I can't have a sine of x value that equals 0. Well, what is that value? We saw that from before. X cannot equal pi n, where n is an element of all integers. Okay, so that's our restrictions to start off for this identity. The right side is the least complicated, so I'll just leave it as is. There's not much to do there. Okay, we might touch it later, but let's take a look. Tangent of x, cosine of x, divided by cosecant of x. Okay, I'm performing operations on the left side, but I don't do the same operations on the right side. Remember, we're proving identities. We're not solving equations. Okay, so one of the first things I can do is I see tangents and cosines. Well, they pair up nicely because I can do this. Sine of x over cosine of x times cosine of x divided by, well, I'm just going to turn that cosecant of x into a sine of x. Okay, so I'm going to highlight what identities I've used. So the quotient identity, and I've used the reciprocal identity. Okay, let's see where that leads us. Cosine of x, cosine of x. So I'm left with sine of x in the numerator divided by 1 over sine of x. And then that is equal to sine of x times sine of x. And that equals sine squared of x. So let me just rewrite it on the last line. Sine squared of x. The right side, let's take a look. Well, it's 1 minus cosine of x, but I'm going to use the identity that 1 minus cosine of x equals the sine of squared of x. So that's my other identity that I'll use. Okay, as you're doing this, it would be handy to have your formula sheet with you, so you can kind of just pick which identities you want to use. So those are most certainly equal, so left side equals right side, and my identities are proven. Okay, but be careful, the identities are valid with the following restrictions. Remember, they're not valid for all real numbers. Here's my restrictions. X does not equal pi n, n is an element of all integers, and x does not equal pi over 2 plus pi n, n is an element of all integers. Okay, so proven identity with restrictions. Next page, folks. Algebraically prove each identity. State any restrictions on the variables. So my restrictions, cotangent of theta, I know that's equal to 1 over tangent of theta, or let me state it as cosine of theta divided by sine of theta. I don't want a sine of theta value equal to 0. So my first restriction becomes from this, theta does not equal pi n, where n is an element of all integers. Okay, that's the first one. The second one I have is from, okay, so my restriction here is I don't want sine of theta equal to 0. Okay, otherwise this cotangent value is undefined. So that's number one. Number two, cosecant of theta. I know that's 1 over sine of theta. I can't have a sine of theta value equal to 0. So let me just restate this. Sine of theta cannot equal 0. Otherwise, cosecant of theta will be undefined. Can't have that. So theta equals pi n. N is an element of all integers. Well, that's the same one we have here. So we have one restriction. Okay, 1 plus cotangent of theta over cosecant of theta equals sine of theta plus cosine of theta. Let's prove this identity. The right side is sine of theta plus cosine of theta. The left side, let's take a look at what identities we can possibly use. So 1 plus cotangent of theta over cosecant of theta. Let me start off with, let me separate the fraction. Let me split it up. 1 over, because I'm seeing this, 1 over cosecant of theta plus cotangent of theta over cosecant of theta. Okay, so small little algebraic step here. 1 over cosecant of theta, that's my reciprocal identity for 1 over cosecant of theta. That is the reciprocal identity. So that's 1 right there. And then plus, let me do some quotient identity. So cotangent of theta is cosine of theta divided by sine of theta divided by 1 over sine of theta. Okay, two more identities I've used. Cotangent of theta as a quotient identity, and then cosecant of theta again as a reciprocal identity. Sine of theta plus, let me divide these two out, sine of theta times sine of theta. That divides out to 1, so I'm left in the last line, sine of theta plus cosine of theta. Well, that equals the right side. Sine of theta equals, sine of theta plus cosine of theta. Left side equals right side. Check. 4 restrictions where theta does not equal pi n, where n is an element of all integers. Okay, so that identity is proven. Next one, cosine of alpha divided by 1 minus sine of alpha equals 1 plus sine of alpha divided by cosine of alpha. Restriction. For this one, I cannot have the denominator be 0, so sine of alpha cannot equal 1. Okay, so where is sine of alpha equal to 1? That would be pi over 2, so alpha cannot equal pi over 2. And general solution 2 pi n, n is an element of all integers, so that's number 1. Number 2, restriction, cosine of alpha, I cannot have that equal to 0, so alpha cannot equal. Where's cosine of alpha equals 0? Well, that's at pi over 2. And that is at pi n, because I can get a cosine of value that's equal to 0 at pi over 2, 3 pi over 2, and every pi units thereafter. So if I combine these two, this would be your overall restriction because this covers that as well. Okay, so I have that as a restriction. Let's rewrite this. Let's start cosine of alpha divided by 1 minus sine of alpha equals 1 plus sine of alpha divided by cosine of alpha. Let me multiply both sides by the conjugate. This is a great time to use the conjugate. 1 plus sine of alpha divided by 1 plus sine of alpha. Okay, this is cosine of alpha times 1 plus sine of alpha, and then on the bottom, the denominator, I have 1 minus sine squared of alpha. And let me use my Pythagorean identity, cosine of alpha times 1 plus sine of alpha divided by cosine squared of alpha. And that's my Pythagorean identity right here and right here. Okay, and then cosine of alpha, and then divides out 1 to 1 with one of the cosines of alpha in the denominator, so I'm left with 1 plus sine of alpha divided by cosine of alpha, and that most certainly equals 1 plus sine of alpha divided by cosine of alpha. Left side equals right side for my restriction that alpha does not equal. So this identity is true with a restriction that alpha does not equal pi over 2 plus pi n is an element of all integers. Example 3. Prove that sine of 2x divided by cosine of 2x plus 1 is an identity equals tangent of x is an identity for all permissible values of x. Hint, you still need to state the restriction. Okay. Here, I don't want this to be 0. So cosine of I don't want that to be equal to 0. So let's solve for x. So that's cosine of 2x equals negative 1. And that's 2x equals inverse cosine of 0. Two x equals, where's cosine of x? What's the inverse cosine of, oh shoot. That's, sorry about that folks, let me back this up. That's not 0, that's 1. Sorry, that's negative 1. Okay, so 2x equals pi. X equals pi over 2 plus pi n, where n is an element of all integers. Okay, so if x equals pi over 2, so let's think about this. If x equals pi over 2, that means that's cosine of pi. Cosine of pi is negative 1, and that makes the denominator 0. So this works, and every plus pi n units thereof. Okay? All right, so there's our restriction. Let's prove this identity. So I have sine of 2x over cosine of 2x plus 1 on the right side. On the left side. On the right side, I have tangent of x. So I'm going to work with the more complicated side, which is the left side. I have a couple of double angle identities. So sine of 2x, I'm going to substitute 2 sine of x, cosine of x. And then cosine of 2x is cosine squared of x minus sine squared of x, and then plus 1. So let me highlight the identities we've used so far. So I have sine of 2x, 2 sine of x, cosine of x, and then cosine of 2x is this first part here, cosine squared of x minus sine squared of x. All right, let's see where that leads us. In the numerator, I'll start with 2 sine of x, cosine of x, divided by, okay, looks like I'll use another identity here. That's cosine squared of x minus 1 minus cosine squared of x plus 1. So I've used a Pythagorean identity to make another substitution here. So this one for this one right here. Okay, so that's another one. Let's continue. That's 2 sine of x, cosine of x, divided by cosine squared of x minus 1 plus cosine squared of x plus 1. Let's keep going. There's my numerator. Cosine squared of x, that's 2 cosine squared of x and negative 1 plus 1 is 0. So that's my numerator and denominator. Okay, 2 divided by 2 is 1. I have cosine of x divided by another one of the cosine of x's. So I'm left with sine of x over cosine of x, and that's tangent of x. So all the way on the right side, let's bring it all the way down. That equals tangent of x for the restriction that x does not equal pi over 2 plus pi n, where n is an element of all integers. Next page. 1 over 1 plus sine of x equals secant of x minus sine of x, secant of x times, or divided by cosine of x. What is my restriction? So this one right here, sine of x cannot equal negative 1. Okay, so where does that occur? X cannot equal 3 pi over 2. That's where x cannot equal 3 pi over 2, and that occurs every 2 pi n units, so n is an element of all integers. The other one is cosine of x equals 0 for this one. Okay, so x cannot equal, whereas cosine of x equals 0, x cannot equal pi over 2, and that's every pi n units, n is an element of all integers, so I have 2 restrictions. Okay, left side, 1 over 1 plus sine of x. That's the simpler side. The right side is actually more complicated this time. So secant of x minus sine of x, secant of x, divided by cosine of x. All right, let's start working on the left side. I'm going to split up this fraction. I have secant of x over cosine of x minus sine of x secant of x divided by cosine of x. Okay, secant of x, I have 1 over cosine of x divided by cosine of x minus sine of x times 1 over cosine of x divided by cosine of x. So what identities did I use there? I said reciprocal identity, and I said another reciprocal identity. Okay. All right, let's continue. What do I have? This is 1 over cosine squared of x minus sine of x divided by cosine squared of x. Okay, because this numerator is sine of x over cosine of x. When I divide by cosine of x, I get cosine squared of x in the denominator. Let's combine those two. 1 minus sine of x divided by cosine squared of x. And this is 1 minus sine of x divided by 1 minus sine squared of x. I'm using my Pythagorean identity here. So transforming it there. Okay, almost to the end. I have 1 minus sine of x divided by, let's factor that, 1 minus sine of x, 1 plus sine of x. And then 1 minus sine of x divided by 1 minus sine of x is 1. And then I'm left with 1 over 1 minus sine of x. Oops, 1 over 1 plus sine of x. Well, that is what our original identity on the right side is, 1 over 1 plus sine of x. Left side equals right side. Check, and just be careful, our restrictions, x does not equal pi over 2 plus pi n, where n is an element of all integers. Well, let me see. The other one, x does not equal 3 pi over 2. Yeah, we can just state this as our single restriction because that will cover all the other restrictions. It will. Every pi units. Okay? Last one, number 5. Okay, left the biggest one for the last here. Prove that sine of 2x minus cosine of x divided by 4 sine squared of x minus 1 equals sine squared of x cosine of x plus cosine cubed of x divided by 2 sine of x plus 1. Wow, big one. Okay, let's state our restriction. Let me state it down at the bottom. Don't have a lot of room here, so give me a second. Okay. Restrictions. That denominator, I cannot have 4 sine squared of x minus 1 equal to 0. So if I solve for this, 4 sine squared of x equals 1, sine squared of x equals 1/4, sine of x equals plus or minus 1/2. Okay, whereas the x value that makes sine of x equals plus or minus 1/2. Well, that is x cannot equal pi over 6 plus pi n, and x cannot equal 5 pi over 6 plus pi n. Okay, so that's one set of restrictions. The other one is, yeah, on the right side, 2 sine of x plus 1. So 2 sine of x plus 1. That can't be 0. So 2 sine of x equals -1. Well, if I look at this, sine of x equals -1/2. If I solve for this, it's already included in that restriction there. So I'm not going to solve this because all of my restrictions are right here. Okay, so there's our restrictions. Okay, and then let's go back and prove this identity. So the left side, this one, remember we said try to work on the one that's technically just work on one side and make it look like the right side. This one is complicated on both sides, so it's going to be hard to make it look exactly like each other. So what I'm going to do is I'm gonna have to work on both sides. So I have sine of 2x minus cosine of x divided by 4 sine squared of x minus 1. On the right side, I have sine squared of x cosine of x plus cosine cubed of x divided by 2 sine of x plus 1. Let me work on the left side first. Double angle identity, so I'm going to go 2 sine of x cosine of x minus cosine of x divided by, let me factor the denominator. That's 2 difference of squares sine, that's 2 sine of x minus 1, 2 sine of x plus 1. Okay, what angle identities did I use? I used double angle identity right here, and I used, that's it, and then the bottom, the denominator, I factored. Okay, let's see where that leads us. Let's see. Well, the numerator, let me factor that further. So that's cosine of x, 2 sine of x minus 1 divided by 2 sine of x minus 1 times 2 sine of x plus 1. Okay, 2 sine of x minus 1 divided by 2 sine of x minus 1, that's equal to 1. So I can simplify it down to cosine of x divided by 2 sine of x plus 1. Okay, I'm going to leave it there. Let me manipulate, or let me work on the right side and see if I can make it equal to the left side. So cosine of x I will factor. So that's sine squared of x plus cosine squared of x. That's the numerator, divided by 2 sine of x plus 1. The numerator, I will use Pythagorean identity. And so let me highlight that right here, right there. And that brings us to cosine of x over 2 sine of x plus 1. And those two are equal. So left side equals right side, with my restriction that x does not equal, right here, pi over 6 plus pi n. And 5 pi over 6 plus pi n. Okay, and that is it, folks. That's the last example, example 5. I would say get lots of practice on proving identities. This is super important for this unit. Um, you got some check your understandings after this, and then there's a whole another section at the very end where I just give you 21 different identities to prove, or prove identities at the end.